Okay, now let's proceed to sequential circuit analysis. So we have our current state given as at t time, and your next state at a time t plus 1 is a Boolean function of your current state and inputs here, right here for the next state. And outputs are Boolean functions of state and sometimes state and inputs. That's it that we need to consider. I mean, when you take a look at this example, for example, what you see here is you need to write everything. Okay, what's your output function and what is your next state function right here? Look at this one. Your output here, your y t is dependent on what? What you see here is a and b, right? A t or bt, and this one is what? Inverse of x, right? X not, for example. Okay, I think this one is I hope this one is correct. And what about your AT1 here? AT1 AT1 is waiting right here, okay? Waiting right here. But what is this, okay? Because at the next clock pulse, this one will be active here. So you focus on particularly what do we have here as the next state. And what is this? It is your x a t plus 1 is xt at, or this one xt bt, right? This one xt bt, right? All right, and you do the same thing for b input, b state as well, and you focus on here. It's a t naught, and this one is your x t here will be your b t plus 1, right? Next state function of b2. That's it. So that's how you build it. I hope I did them. All of them are correct. As you see, you focus on the this is the input to next state of A, this is the input, combinational logic input to next state of D, and this is the combinational logic of for Y. See that this all make up the combinational part of your sequential circuit, and these are your storage elements. Storage elements here, and this is your combinational logic part. If we return to right here, these are your storage elements here, and this is your combinational logic part. That's it. Okay, hope you have an idea. Okay. So when you put this in a computer-aided simulation tool or something, you send your clock signal here, you provide your inputs, next state function for A and B, and your current states, and this is your output. And with each, let's say, pulse of the clock, suppose that, as you see, when our states and outputs are updated here, look at this, at the rising edges of the clock, right? So it means that we're using a positive edge triggered system here, and you can see how your system behaves for testing purposes in your own studies. So the state table is what we need here. Instead of truth table, we will have a state table here. It's pretty similar to a truth table that we have discussed in combinational logic part, but this is what we need here. We need a state table. It's a multiple variable table with the following four sections. You have present state and inputs here as the input part, and next state and output part as the output part. So as you see, these are the inputs and these are the outputs. Okay, if you look at it as a truth table thing. And when we return to our example, you can represent this Boolean functions just like this in a truth table by giving all the combinations right here. See how it's convenient. These are your inputs on the left hand side. These are your inputs and these are your outputs. You see your current states and input and your next states and output. But you can show it in a much better way, which is your alternate state table. I prefer this one because it's easy to understand. You put your present state and next state and output in columns here like this. You can have 0, 0, 0, 1, 1, 0 and 1, 1 like this. And if your x input is 0, you will go right here to these states. And if your x input is 1, you will go here, right here, this state. So it helps us to maybe understand or maybe make a correspondence to state diagrams as well later. And again, you have the same structure for the output as well. It depends on your present state and your input as well, and this will be your output. You just redesign or reshape your paper, this table in this manner. This is much more convenient. Okay. But what about the state diagrams? The sequential circuit function can now be represented in a graphical form as well, which is called a state diagram, where you represent all of those states with a circle. So your 0, 0 state will be a circle here, a directed arc from the present state to the next state for each state transition from a state to another. And a label on each directed arc shows us which input values are required for the transition, like x equals 0 or something like this. And a label on each circle, for example, you can do it like this, and with this input, the output will be also 0 or something. Or you can write it like this with, for example, in 0, 0 state, your output is 0. And at 0, 1 state, your output will be 1. You can represent it like a Moore machine or Mealy machine in this manner. So, if outputs are included on the states as well, like this is called a Moore type machine or Moore type state diagram. And if your outputs are, as we just discussed, x equals 0, y equals 0, it means that you're talking about a Mealy type state diagram here if your outputs are on the arcs. Now look at this state diagram right here. Again, we still deal with our initial example here. Look at this one. Okay, look, when I'm at 0 state, if I receive x equals 0, I will go to 0 state again by giving the output 0. But if I'm in this state, 0 state, if I get an input of 1 here, I will move to 1 state by giving the output 0 again. Look at this. That's what we have here. That's it. You see, if I'm at this state, if I get 0, give this output and the output will be 0. But if I get 1 here, I will move to this state by giving 0 output again. That's the idea. Okay. So what type of diagram is this? Since our outputs are on the arcs, this is a Mealy type state diagram here. Those diagrams, state diagrams, can get confusing for large circuits, but we won't have any large circuits in our exams or something. We will have small circuits, and they're usually easier to understand than the state table for smaller circuits, because you can see what's going on here. They are especially useful for your designs that we will discuss later. So when we talk about the equivalent states, the two states are equivalent if their response for each possible input sequence is an identical output sequence. It means that if they're equivalent, you don't need both of them. Either of one of them will be okay. So you can cancel one of them. Alternatively, two states are equivalent if their outputs produced for each input symbol is identical, and their next states are for each input symbol are the same or equivalent. Let's take a look at this. What you have here is, let's take a look at this in this manner. If I'm at S2 state, if I receive 0, I will go right here as 0 by giving 1 output. All right. If I get 1 output here, I will stay here by giving 0 output. Okay. Now let's take a look at S3 now. Don't forget about S2. If I get 0 here by giving output 1, I will end up here. The same. You see, and if I get 1 here, I will give 0 output and I will end up here. Okay, they are equal again. So I can comfortably say that I don't need this one. Okay, or I don't need S2 here. I will just put this one and like place it on this one. Okay, now this one becomes S2, and you don't have these arcs anymore because you don't need them. Okay, but of course you need to keep this 1 0, right? Because you put this like this. Okay, now take a look at this one again in the same manner, S1 and S2 now. So if you get 1 and you give 0 output and you're here, if you get 1 0 output and you're here, okay, check. How about this? If you have 0 input, you give 1 output and you're here. If you get 0 and you, okay, I don't need this one as well. Okay, so then what I do here is, now I push this one, push this one over this one, and now this becomes S1 with 1 0 turning over this one, and you cancel the S2 right here. I think it makes sense, right? That's the idea about how you get rid of the initial states and take those steps. I hope you understand that those type of questions can be asked to you in the exam, or when you design your circuit, you can realize this and end up with simpler circuits. We will discuss more about this in the sequential design part as well. This part will be dealing with, the current part will be dealing with the sequential analysis only for the moment. The Moore and Mealy models are two choices for your sequential circuit designs, and maybe you remember this from finite state machines, or I think you have discussed about this in theory of computation or something like this. I remember from that course as well. The Moore model is named by the Moore, and outputs are a function of only states, and the Mealy model is named after G. Mealy, and outputs are a function of inputs and states. So the outputs are put on the arcs. When you pause the video and think about this, you can easily see that the Mealy model is much more, I mean, prone to errors because there can be glitches in your inputs right here. So your inputs will affect your outputs in a very, I mean, direct manner here in your Mealy designs. But in Moore type states, since your system is giving output signal or changing its output signal, as long as it is settling in a specified state here, you can see that Moore models are much more reliable. Maybe, I mean, Mealy model can be much more straightforward, but you should keep in mind that Moore models are easy to code or easier to implement, and usually hardware systems are generally based on Moore models by means of or taking the reliability issue into consideration. But best choice is mixed models, of course. You depend on which are the critical parts, critical outputs, critical states, and you optimize the system. So the more is more, you can remember this. Always a system that does the same thing. The Moore version has more states than the Mealy one usually. Here you have this one. See, if you want to implement this as a Moore machine, you need to have an extra state here, which is namely your state 2 here, because your outputs cannot be put on the arcs. That's why. Okay, that's how you implement it. Okay, that's the because distinction here. Because x is 1 and y is 1 sends you to state. X is 0 because y is 0, it will send you another state. You cannot represent this difference in Moore with only 2 states. You need an extra state for representing this one. That's it. And since this state is represented like this, you can obviously see that it is returning to 0 with like this, you see, to 0 in both types. So these are the state table maps to state outputs, just a representation, that's it. And this is the Mealy model state table maps the inputs and state to outputs. You can also have mixed models. We just talked about this. As you see, this one is a mixed state diagram here. The first one is a Moore state. Look at this, it's pretty interesting. And these ones are Mealy states. As you see that their outputs are effective right here. But in this Moore state, no outputs on the arcs of this, I mean, Moore state. Now, let's try to analyze this sequential circuit. What is going on here? Okay, now you can see that your ZT is AT directly. If you put this in a box, there are no inputs here, maybe you noticed, but it's working like this. And what is your AT plus 1? AT plus 1 is, as you see, it is B, C, BT, CT. And what is your BT plus 1 here? BT plus 1 here. BT plus 1 is, what is this? It is, this one is C, and this one is B naught, BT naught, CT, and this one is BT again, and this one is CT0 plus PT CT0, I think. I hope I don't make any mistakes, but you double check yourself. And how about CT plus 1 here? CT plus 1 is this one, which is your CT0. That's right, I think. And this one is AT0. AT0. Okay, let's see if we let's just write them like here. I won't put the T's here. It's BC and B0 C plus BC0, and this is your A0 C0, and that would be your A. And this is the direct inputs to your circuit. It means that your circuit is reset to 0, 0, 0 for each of these particular flip-flops here. You remember this? The direct inputs, right? How can we do this? With the help of direct inputs. Where are they? Direct inputs? Right here. By using direct inputs, you can set them to start from 0 by providing 0 signal to reset right here. Alright, so this is what your state. Okay, when you fill this state table here by just putting their corresponding values, for example, for A, while it is BC, it means that it will depend on it. And when you fill this table with corresponding values here, it will look like this: 0, 0, 1, 0, 1, 0, with 0 output, 1. But I suggest you to double check it yourself as well. So 1, 1, 0, 1, 0, 0, 0, and 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and 1, 0, 0, 1. Alright, so as you see, I start from this state and then I move to this state by giving 0 output. Okay, then move to this state giving 0 output, move to this state giving 0 output, and I will now move to this state by giving 0 output. I will move to this state by giving 0, and I will move to this state. You see, if you want to put this in a state diagram here, it would look like this. When you reset, you start from here, then with each step you go right here, go right here. These are your outputs as well, you see, and then you go right here, then you go right here and come back. Okay, see, your Z output is 0, 0, 0, 0, and 1 here. So your Z output here is, if you put them like a Moore machine, 0, 0, 0, and 1 here, right? If you look at this, it's only 1 in that particular state. And let's try to answer those questions. Which states are used here? So you see, these 5 states are used here, the first 5 states. And what about the others? They theoretically exist, but we never end up with those states, so they are not used. Okay. These states are not used here, only 5 states are used. And what is the function of the circuit? Just pause the video and think about it. Look at this. It gives us, one signal, like it gives us one output at every 5 clock cycle, right? Like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Except the start where you get one output after 4 clock cycles. Isn't that right? If you start it right here, it means that you will get the first one, only the first one in 4 clock cycles, right? 1, 2, 3, 4. See? And then after this, after the first turn, your circuit will behave giving one output every 5 clock cycle, like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, or something like this. Okay, this is all about the sequential circuit analysis part. Of course, maybe this was a bit boring, but in the next part we will deal with the sequential design, and it is much more interesting, I hope. Okay, thank you for listening.